So far, we've seen a couple of examples of activators and deactivators for electrophilic aromatic substitution. In today's video, I want to go over how you can recognize these substituents and summarize their effects on both electrophilic aromatic substitution and the acid-base properties of some of these molecules. So let's start with taking a look at a substituted benzene. And anytime we are trying to determine if a substituent group is an activator or a deactivator, we're going to be interested in the atom that's directly attached to that carbon or to the aromatic ring. So if that atom has some lone pairs on it, then it is likely a pi donor. So one example that we have seen so far is oxygen, and we've seen it as an O-methoxy or an OH. Another example might be an amine like aniline if that was attached. We could also look at amides. So rather than the amine or the NH2, we're going to have some amide attached. Or an ester. All of these atoms, the oxygen has 2 lone pairs, a nitrogen has 1 lone pair. All of these atoms have a lone pair, and they can donate some electron density into the aromatic ring through resonance. So if we assume X has some lone pairs, it can donate electrons into this aromatic ring through resonance. And that will ultimately mean that the Wayland intermediate created in electrophilic aromatic substitution is stabilized through an extra resonance contributor. Sometimes we've seen a sigma donor, and the primary sigma donor that we have seen is a alkyl group, like a methyl group. So if we put a CH3 there, the intermediate, the Wayland intermediate, when it's a methyl group, is still stabilized because you create a tertiary carbocation, but it's not stabilized through resonance. Another example of a sigma donor is a phenyl ring. While phenyl rings look like they might have resonance stabilization, the problem is that when you think about a phenyl ring attached to another ring, these rings are not in the same plane. And so there's not much resonance involved. They have to be out of different planes because these 2 hydrogens here would be occupying the same space if they're in the same plane. And so phenyl is actually a sigma donor, not a resonance donor. Halogens were an exception that we saw. Halogens like fluorine, chlorine, bromine, and iodine, they have lone pairs, but these are deactivators. Because they have lone pairs, these are going to all be orthopara directors. So everything that we've drawn so far is an orthopara director. And the ones in red are activators. They increase the rate of electrophilic aromatic substitution. because they have resonance, halogens are also orthoparadirectors, but these are deactivators. Activators we will sometimes call electron donating groups. Deactivators are going to be electron withdrawing groups. So halogens were the exception. They have electrons, which means they can donate electrons through resonance, but they are highly electronegative. And so they inductively withdraw electrons from the aromatic ring, and so they're net electron withdrawing groups. Other examples of deactivators that we have seen include carbonyl containing compounds, so ketones, aldehydes, esters, and amides are all carbonyl containing compounds, and they are deactivators. Notice that an ester and an amide can be both an activator and a deactivator. It depends on how it's attached to the aromatic ring. So if we look at the aromatic ring and the carbonyl is directly attached to the benzene, it is a deactivator. If, on the other hand, the oxygen or the nitrogen, if it's an amide, is connected to the aromatic ring, there's lone pairs on the atom directly attached to the aromatic ring, and so it's a activator when it's in this configuration. And then some other examples of deactivators we've seen, a nitro group. This has a nitrogen, but remember that nitrogen has no lone pairs on it because it's got a formal positive charge, and so it's a deactivator. CF3 looks like an alkyl group, but because fluorine is so electronegative, it's a net deactivator. Nitriles, C triple bond N. Sulfates or sulfonic acids, those are all electron withdrawers. They are meta-directors. And they're deactivators. These groups are deactivators because the atom attached to the aromatic ring doesn't have any lone pairs, and they're connected to very electronegative atoms. So these are inductively electron withdrawers. So to summarize, if your atom has a lone pair that's directly attached to the aromatic ring, is going to be a resonance pi donor. It's an orthoparadirector and an activator. Alkyl groups are activators, and they are sigma donors. Halogens are deactivators because they're so electronegative, but they do have lone pairs, and so they're orthoparadirectors. If the carbon is directly attached to the aromatic ring, remember that this carbon has no lone pairs and oxygen's electronegative, and so it's going to inductively withdraw electron density away from the aromatic ring. The same is true for these other groups. The atom directly attached to the aromatic ring doesn't have any lone pairs, and the next atom is very electronegative, and so it's going to inductively withdraw electrons away from the aromatic ring. Electrophilic aromatic substitution can also be conducted on multiply substituted aromatic rings. And so if we look at this compound, metaxylene, where you have two methyl groups that are meta from one another, and we think about the nitration of that compound. This position here is ortho to both positions, and so methyl groups are ortho para directors. That is a good thing. This is ortho to both. This position is ortho to one and para to the other. And this position is also ortho to one and para to the other. The last option here is meta to both. Since methyl is an ortho para director, we can rule out the meta position as a primary spot of nitration. This position is not bad, but sterically it's congested by both methyl groups, and so sterically this is not a good option. Electronically, this option and this option are the same, and they're sterically available. And so the major product of this reaction is going to be nitration at this position. If you were to think about drawing the other position here, hopefully you notice that these are the exact same molecule, and so the major product is just this, and there are two ways that you can form it. Sometimes, however, the directing capabilities or directing groups are pointing at different positions. So if we look at meta-nitroanisole here, the O-methoxy group is pointing ortho and para, and so it wants to add here, here, or here. The nitro group is pointing to the meta positions, and so this is the only meta position available. Anytime you have conflicting directing groups, the activator or the most activating group is always going to win. And so I'm going to focus on the positions that the O-methoxy group is going to donate or be directing. And so it's directing here, here, and here. Again, this spot position is sterically hindered, and so probably not much is going to add at that position. But both the ortho and para positions here are likely a point of addition. And so I would expect the major products of this reaction to be adding a nitro group there and adding a nitro group here. It's difficult to say which one of those is major, but you would definitely have a mixture of those two. Substituents on benzenes can also affect the pKa or the acidity of other functional groups. And so if we look at these substituted benzoic acids, you'll see that the electron-rich benzoic acid has a pKa of about 4.47, and the highly electron-poor benzoic acid has a pKa of about 3.44. Remember that pKa is a logarithmic scale, and so that means that the electron deficient para-nitrobenzoic acid is about 10 times more acidic than the electron rich para-methoxybenzoic acid. If we want to understand more about why the electron rich benzoic acids are less acidic than the electron poor benzoic acids, we've got to consider the conjugate base. And so let's draw the conjugate base of para-methoxybenzoic acid. The most acidic proton in this compound is, of course, the hydrogen attached to the carboxylic acid. So we're going to pull that off. And that's going to leave a minus charge. Now we said that this methoxy group is electron donating. This is an electron rich benzoic acid, and so I want to show some resonance with this lone pair getting pushed into the ring and that bond being moved to a carbon. So we wind up with something that looks like this. And we can keep pushing those electrons around. Forgot my positive charge over here. Like so. If we compare that to nitrobenzoic acid, again, we need to look at the conjugate base. This time we can withdraw electrons from the ring by taking that pi bond there and moving some electrons onto oxygen. Oop, we broke that bond. And we can move it one more time. Like so. Now it's tempting to take this bond right here and bring it down to have resonance stabilization of this carbocation from that pi bond. But that's going to take away an octet from oxygen, and we're never going to do that. These are not resonance stabilizing this negative charge up here. But if we look at the nitro group, it is inductively withdrawing electron density out of the aromatic ring. I've got a positive charge floating around inside my aromatic ring, which is inductively withdrawing electron density away from this minus charge. If this minus charge is delocalizing electrons or is delocalized towards the aromatic ring, it's harder to find, and so it's less likely to pick up a proton, which means it's a worse base than the methoxy group. If this is a worse base, that means this conjugate acid is a stronger acid. Conversely, this methoxy group is pushing electron density into the aromatic ring, and so this methoxy group is destabilizing this extra minus charge, and so this methoxy group is less stable. It is a better base, and so it wants to pick up this proton more, and so it's a weaker acid. Substituents can also affect the pKa of phenols. If we look here, paramethoxy phenol has a pKa of about 10.2, whereas paranitrophenol has a pKa of 7.14. So in fact, the substituents of phenols affect the pKa even more than they did of a carboxylic acid. There's over a 10 pKa unit difference, which means this paranitro-benzoic acid is about 1,000 times more acidic than paramethoxy benzoic acid. Again, if we want to understand more about why that is, we've got to look at the conjugate base. Anytime we're thinking about acidity, organic chemists like to think about the conjugate base. Specifically, we like to think about the Lewis definition of the conjugate base and how well it can donate electrons. If we look at the conjugate base, the proton on the oxygen is going to be the easiest one to deprotonate, which will leave us with this O minus. Then methoxy again is a resonance donor. We can donate electrons into the aromatic ring, like so. And that charge can bounce around the aromatic ring. To generate these resonance structures. Here. And since methoxy is electron donating, we're pushing electrons towards the O minus, and specifically this resonance contributor, which is missing a positive charge. This resonance contributor here, where you put two minus charges right next to each other, is making this oxygen really want to give away electrons more, and so it's making this a stronger base or a weaker acid, or the phenol is a weaker acid because these electrons are ready to be given away. On the other hand, if we look at the nitrophenol and its conjugate base, where you've lost a proton, here again, the nitro group is a resonance electron withdrawer, so I can pull these electrons here and create this resonance structure. And then that positive charge can bounce around the aromatic ring. Here, and this time, this oxygen and this positive charge can communicate. And so I've got a resonance structure where these electrons are coming down and forming a double bond to generate this resonance structure. And of course, we can bounce that positive charge one more time around the ring. It requires 2 arrows from that resonance structure to get to this. Here. And so the nitro group is electron withdrawing, and it has a resonance structure in which the O minus charge is gone and placed down here. And so this pair of electron is delocalized, they're distracted, they're harder to find, and so it doesn't want to give away a pair of electrons to protonate, and so this is a bad base, which means it is a stronger acid. We're going to wrap up today's video there. We'll talk more about multiple substitutions next time.